Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will see the subfamily of the TTL logic and we will see that how the TTL logic evolved over the time and how the different versions of the TTL came into existence. So far, all the discussion related to the TTL logic which we have carried out that was for the standard TTL version which is often known as the 74 series. So for example, the 7400 is the IC for the standard TTL 2-input NAND gate. And likewise, the 7404 is the IC for the inverter. So after the standard TTL gates, the different versions of the TTL also came. So the main purpose of all these different versions was to either reduce the power consumption or to increase the speed of the TTL gates. So if you see the typical power consumption of the TTL gate, then that is roughly around 10 milliwatt. While if you see the speed or the propagation delay of this logic gate, then that is roughly around 9 to 10 nanosecond. So all the versions that came after the standard TTL gates have either a lower power consumption or the higher speed compared to the standard version. So during our discussion, we will take the reference of the standard 2-input TTL NAND gate. And with respect to that, we will see that what modifications were made in the different versions of the TTL. So the first two series that came after the standard 74 series were the 74L and the 74H. So if you see the 74L series, then that is the low power TTL logic. So the design wise, it is same as the standard TTL logic. But here, the resistor values were increased. So because of the increase in the resistor values, the current drawn by the circuit will also reduce. And because of that, the power consumption of the logic gate will also reduce. But at the same time, because of the lower current, the capacity load at the output also charges slower. So if you see the typical power consumption of the 74L series gates, then that is around 1 milliwatt. So as you can see, compared to the standard 74 series version, there is a substantial reduction in the power consumption. But at the same time, the speed will also reduce. So here, the propagation delay is roughly around 33 nanosecond. So that is the 74L series. That is the low power TTL logic. So then after, to increase the speed of the logic gates, the 74H series came, which is also known as the high speed TTL logic. So in this version, the values of all the resistors were reduced. And because of the lower resistance values, the current in the circuit increases. And due to the higher current, the capacity load charges faster. And due to that, we will see the increase in the speed of the logic gate. And further, to increase the speed, here on the output side, the Darlington pair is used. So as you know, this Darlington pair provides the higher current gain, that is roughly equal to beta square. So when this Darlington pair is in the on condition, then due to this higher current, the capacitive load at the output charge is faster, and hence we will have the faster turn on time. So if you see the same thing in the other way, then the output resistance of this Darlington pair is even lower. So due to this lower resistance, the RC time constant will also reduce, and hence we will have the faster turn on time. Now here, the purpose of this resistor at the emitter of the Q4 is that when this Darlington pair goes in the off condition, then the charge that is stored at the base of this Q5 will remove through this resistor. So in short, because of this Darlington pair at the output side and due to the lower resistance values, the propagation delay of the 74H series gates is lower compared to the standard TTL gates. But due to the higher current, the power dissipation will be more. So here, for the 74H series, the typical power consumption is around 23 milliwatt. While if you see the propagation delay or the speed of the logic gate, then that is roughly around 6 nanosecond. So for any logic gate of any family, the important metric to measure its speed and the power efficiency is the speed power product. And as its name suggests, it is the product of the average power that is consumed by the gate and the speed of the gate. So this parameter defines the energy consumed by the logic gate per switching operation. and often it is represented in the picojoules. So the lower value of this parameter indicates the better efficiency of the logic gate. So for the 74H series, if we see the speed power product, then that is around 138 picojoule. And in fact, that is even higher than the standard TTL gate, because for the standard TTL gate, this typical speed power product is equal to 90 picojoule. So of course, the 74H series gates provides the better speed, but they are not efficient in terms of the power. So then after, to improve the speed and the overall efficiency of the gate, the 74S series came into existence. And this series uses the Schottky transistors. So first, let us briefly understand what is Schottky transistor. And in the 74S series, why the normal bipolar junction transistors were replaced by the Schottky transistors. So here, if you see the standard TTL logic or even the 74L and the 74H series, then in this series, the majority of the transistors in the circuit were operating in the saturation. So in the saturation, the excess amount of charge is stored in the base of the transistors. So unless this charge is not removed, the transistor won't go in the off state. And that delay in the removing the charges from the base of the transistor limits the speed of the logic gate. So if you see the Schottky transistors, then they uses the Schottky barrier diode between the base and the collector of the transistor. So this arrangement does not allow the transistor to go into saturation. And in this way, that eliminates the problem of the excess charge that is stored in the base of the transistor. So here, when the sufficient amount of base current starts flowing through the transistor, then the transistor starts going into saturation. And due to that, this voltage Vc starts reducing. So here, as soon as this collector voltage starts dropping, the Schottky barrier diode will get turned on. And as you know, the forward voltage drop of the Schottky barrier diode is around 0.25 to zero point 0.3 volt. Because if you are aware, the Schottky barrier diode has the metal semiconductor junction. So once it gets turned on, then the voltage difference between the base and the collector will remain between the 0.25 and the 0.3 volt. So for example, if the voltage at the base is equal to 0.7 volt, then the voltage at the collector will be around 0.4 volt. And hence, in this case, this base collector junction will not get forward biased. Because as you know, for the transistor to go into saturation, both base emitter and the collector base junction should get forward biased. But in this case, this collector base junction will not get forward biased. And in this way, the transistor won't go into saturation. So we can say that in this way, the Schottky barrier diode prevents the transistor from going into saturation. So these transistors with the Schottky barrier diode are known as the Schottky transistors. And typically, this is how they are represented. That means this is the symbol of the Schottky transistor. So the 74S series uses this Schottky transistor. And this is the circuit of the 74S series 2 input NAND gate. And this TTL series is known as the Schottky TTL Logic. So as you can see over here, except the one transistor in the Darlington pair, all the transistors have been replaced by the Schottky transistor. And that prevents all the transistors from going into saturation. And due to that, there will be an improvement in the speed. Moreover, compared to the standard 74 series TTL logic, here all the resistor values have been also reduced. So due to that, the overall current in the circuit will increase and hence the capacitive load will charge faster. And due to that, we will also see the improvement in the speed. So apart from that, on the output side for the active pull-up, we also have the Darlington pair. So as we have discussed earlier, when this Darlington pair is in the on condition, then it offers the very low output impedance. And hence, during the low to high transition, this capacitive load will charge faster. And because of that, there will be an improvement in the speed. So similarly, here for the pull down also, we have the active element. So if you recall that in the standard TTL logic, during the pull down, we had only resistor over here. And we have seen that that resistor helps in removing the charge that is stored at the base of the transistor. So in this case, since we have the active element, so it removes the base charge of the transistor even faster. Moreover, here now since all the transistors are the Schottky transistor, so they won't go into saturation. And because of that, there won't be a much base charge compared to the earlier case. So let us understand how this active element in the pull down network helps in increasing the speed of the logic gate. So in this logic gate, during the low to high transition, this Q4 and Q5 will be in the on condition, and at that time this Q6 will go into off state. So this Q6 transistor will completely go in the off state when the charge that is stored at the base of the transistor will get removed. So here, when this Q6 starts going into the off state, at that time this Q3 is already in the on state, and hence it provides the lower resistance path for removal of this base charge. And due to that, we will get the faster low to high transition. Apart from that, this transistor Q3 also helps in faster high to low transition. Or in other words, I would say that it helps in turning on this Q6 transistor during this high to low transition. So in the standard TTL gate, we have seen that when this Q2 transistor gets turned on, then the current through the emitter will get divided in the two branches. The one current will flow through the resistor, while the other current will go into the base of the another transistor. But in this case, if you see, then instead of the passive resistor, here we have the active element. So it won't get turned on until there is a sufficient voltage at the base of this Q3. That means until this Q3 gets turned on, this Q3 transistor will not draw any current, and therefore this entire current will go into the base of the Q6, and due to that this Q6 will turn on faster. So in short, because of this Q3 transistor, this output transistor Q6 can get switched on and off faster. Moreover, here because of this Q3 transistor, we will also get the sharper voltage transfer characteristic. So this is the voltage transfer characteristic of the standard TTL inverter. So as you can see, during the high to low transition, here we have the two slopes. So in this region, only this Q2 transistor will be in the on condition, while in this region, both Q2 and the output transistor both will be in the on condition. But in this case, we will not have that situation, because in this case, when the voltage at the base of the Q2 reaches the 0.7 volt, at that time it won't get turned on, because unlike the earlier case, here we don't have any passive resistor. So now, to turn on this transistor Q2, we also need to turn on either Q3 or the Q6, and for that we also require the additional VBE. That means here, to turn on this transistor Q2, we require the 0.7 plus 0.7 volt at the base of the Q2. That means when the voltage at the base of the Q2 is around 1.4 volt, at that time this Q2 will get turned on, and at that voltage this Q6 will also get turned on. That means in this case both Q2 and Q6 will get turned on simultaneously, and due to that now this curve will get stretched up to the 1.1 volt, and therefore now we will have the sharper transition. So these are the advantages that we will get after adding this Q3 transistor. So apart from all these changes compared to the standard TTL version, here we also have the Schottky diodes at the input side. So these diodes provides the negative voltage protection, and it also removes the ringing. So because of all these design changes, we get the improvement in the speed. But due to the lower resistance values, the power consumption will increase. So for the 74S series, the power consumption is around 20 milliwatt. While if you see the speed, then that is around 3 nanosecond. That means compared to the previous versions, there is a substantial improvement in the speed, and therefore the speed power product will be equal to 60 picojoule. So that is the Schottky TTL logic. So after the 74S series, to reduce the power consumption of the gate, the 74LS series came, and that became quite popular. So the 74LS is the low power, slower speed version of the 74S series. And here, this LS stands for the low power Schottky TTL logic. So in this version, the manufacturing technology was also changed. That means in this version, the size of the transistors was also lesser compared to the earlier version. And because of that, the parasitic capacitance were also reduced. And hence, there was also increase in the speed. But here, since it is a low power version of the 74S series, so here the value of all the resistors were increased. Apart from that, there are couple of more changes on the design side. So here on the input side, instead of the multi-emitter transistor, we have a simple two Schottky diodes. The reason is that the Schottky diode requires a much lesser space compared to the conventional multi-emitter transistor. And the second reason is that here since we have the Schottky transistors, so they are not going into saturation, and therefore the charge at the base of these transistors will also be less. So it can easily be removed with the help of these Schottky transistors. And therefore here these two Schottky diodes are used for the two inputs. So whenever the inputs are low, at that time the current will flow through these Schottky diodes, and it will also remove the base charge of this Q1 transistor. That means whenever these inputs are low, then these Schottky diodes will get turned on and it won't allow the Q1 to go into on state. And whenever the inputs are high, at that time the Schottky diodes will remain in the off condition and the Q1 will get turned on. So that is one of the modification in this 74LS series. Apart from that, here we also have a two more Schottky diodes. So here this upper Schottky diode helps in removing the base charge of the Q5 when it goes from the on to off state, because here this Schottky diode provides the path for removal of the base charge of the Q5. So when the Q5 goes in the off state, at that time this Q1 will be in the on condition. So through this path, the base charge of the Q5 will get removed. So that is the purpose of this upper Schottky diode. And this lower Schottky diode provides the additional sink current path through this Q1. So whenever the output goes from the high to low state, at that time this capacitive load will get discharged through this transistor. But now it will also have the additional path for the discharge through this Schottky diode, and hence it will also turn off faster. And because of that, we will have the faster turn off time of the logic gate. So here, due to all these modifications, despite increasing the resistor values, the speed that we are getting is comparable to the standard TTL gates. So of course, here since the resistor values have been increased, so the power consumption will be low. So for the 74LS series, the typical power consumption is around 2 milliwatt. While if we see the speed, then that is around 10 nanosecond. That means now the speed power product is equal to 20 picojoule. And if we compare it with the standard TTL logic, then that is almost 4 to 5 times lower. So that is the 74LS series of the TTL gate. So after the 74LS series, the 74ALS series came. That is the advanced low power Schottky TTL logic. So compared to the earlier version of the 74LS series, this version was using the 3 micron fabrication technology. That means here the transistor sizes were further reduced. Apart from that, there are a couple of changes in the design which reduces the power consumption and increases the speed of the logic gate. So the first one, if you see, then there is an additional transistors over here. So this transistor provides the required base drive for this Q2 transistor, because now the emitter current of the Q1 is going as the base current for the Q2. So due to that, now the base current of the Q2 will increase, and due to that, now this Q2 and Q3 will get turned on faster, and that will improve the switching speed. So apart from that, if we see the second change, then now on the input side we have the PNP transistors. So first, let us understand why these transistors were introduced. So here, due to this additional Q1 transistor, to turn on this Q2 and the Q3 transistor, we require the additional voltage of 0.6 to 0.7 volt. That is the VBE of the Q1, right? That means due to this additional transistor, the voltage at the base of the Q1 should be at least 3 VB drop. That is the 1 VB plus the second VB and the third VB. So due to this additional transistor, the required input voltage to turn on this Q2 and Q3 will also increase. But to compensate that, here these PNP transistors were introduced. So here, these transistors are used in the emitter follower configuration. So here, for these PNP transistors, this VB drop will be negative, that is equal to minus 0.7 volt. And due to that, this additional VB drop will get eliminated, because here we are applying the input at the base of this PNP transistor. So now if we see, then the required input voltage to turn on this transistor Q2 and Q3 will be equal to minus 0.7 volt plus the 3 VB drop across these three transistors. That means here this additional VB drop will get eliminated, and therefore the required input voltage will almost remain same. So that is the purpose of these PNP transistors. Moreover, here these Schottky diodes were introduced to remove the base charge of this Q2 transistor, and due to that it will get turned off faster. And finally, since it is a low power series, so to reduce the power consumption, all the resistor values have been increased. So for the 7.4 ALS version, the typical power consumption is around 1.2 milliwatt. And if we see the speed, then that is roughly around 4 nanosecond. That means the speed power product is equal to 4.8 picojoule. So that is the advanced low power Schottky TTL logic. So after the 7.4 ALS series, the 7.4 AS and the 7.4 F series came. So these versions are basically a faster version of the 7.4 ALS series, which mainly focuses on the speed of the TTL gates. So here, this AS stands for the advanced Schottky TTL logic. So in this version, the typical power consumption is around 8 milliwatt, but the speed of the logic gate is around 1.7 nanosecond, and it is fastest among the all TTL versions. So therefore, here the speed power product is around 13.6 picojoule. And then the 7.4 F series is also very similar to the 7.4 AS series, but this version was developed by the company called Fairchild. So if you see the characteristic of the 7.4 F series gates, then that is comparable to the 7.4 AS series. And that is how, over the years, the different versions of the TTL came into existence. So still in many applications, these TTL logic ICs are used for the prototyping. But in most of the applications, nowadays, this CMOS logic is used, because this CMOS logic is very power efficient and it is also very easy to scale it up. So the issue with the TTL logic is that it is not easy to scale it up, because as you know, this TTL logic involves a lot of resistors and the transistors. So during the fabrication, this resistor takes a lot of space, and hence using this TTL logic, it is not possible to design the very large scale integrated circuits. And that is why over the years, the CMOS logic has replaced the TTL logic. So that's it for this video, and I hope in this video you understood the different versions of the TTL logic and how this logic evolved over the years. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.